This video took me more than 10 years to make. Its story began when I was in high school. I was mystified by the sinA-B formula. Specifically, two things caused me discomfort. One, from where do cos A and cos B show up in sine of A minus B expansion? And to complicate things further, why is sine of one angle, say A, multiplied by the cosine of the other angle B? After many years, I found an acceptable answer. Surprisingly, although sine and cos are defined on circles, an answer to these questions are not rooted in the circle. Rather, we find an answer to these mysteries in the area of the parallelogram. So let's explore that. Suppose we have two two-dimensional vectors x1, y1 and x2, y2. Let's add a copy of the vector x1, y1 to the end of x2, y2. And let's add a copy of the vector x2, y2 to the end of x1, y1. And now we have a parallelogram. And our interest is in finding the area of that parallelogram. To do that, we first draw the surrounding rectangle. The surrounding rectangle is in yellow and has length x1 plus x2 and height y1 plus y2. So the surrounding rectangle has area x1 plus x2 times y1 plus y2, which is x1 y1 plus x1 y2 plus x2 y1 plus x2 y2. And notice that in this expression, we have two terms that depend on both vectors, which is x1 y2 and x2 y1. What's between the surrounding rectangle and the parallelogram? We have one blue triangle of area x1, y1 by 2. And we have another blue triangle of area x1, y1 by 2. And both these triangles depend only on the vector x1, y1. We have one red triangle of area x2, y2 divided by 2. And note, this area depends only on the coordinates of vector 2. And another red triangle of area x2, y2 by 2. Now comes the interesting part. We have one purple rectangle of area x2, y1. This area depends on both vector 1, which gives us the y1 coordinate, and vector 2, which gives us the x2 coordinate, and this is at the heart of our mystery. And we have another such purple rectangle of area x2, y1. So the area of the purple rectangles is 2 times x2, y1. Now the area of the parallelogram is area of the surrounding rectangle minus 2 times the area of red plus blue triangles minus 2 times the area of the purple rectangles. And that works out to be x1, y2 minus x2, y1. We are seeing x1 multiplied by the other vector's y2 coordinate. And similarly, we have x2, y1. That's neat, but what does that have to do with sine of A minus B? We'll get to that very soon. On the unit circle, let's draw a point at angle A. The coordinates of this point are cos of A and sine of A, and the red line has length 1. Let's draw another point at angle B. The coordinates of this point are cos of B and sine of B, and the blue line is also the radius, and since it's a unit circle, that too has unit length. The angle between A and B is, of course, A minus B. Let's attach at B a copy of the line from the center to A, which is the red line, and attach at A a copy of the line from the center to B, the blue line. And let's focus on the quadrilateral we formed. The base of the quadrilateral goes from origin to cos B sine B and is of length 1. The height of the quadrilateral, which is the distance from A to the blue line, is the length of the red line times sine of A minus B. But the red line has unit length, so the height is just sine of A minus B. So the quadrilateral area is sine of A minus B. Let's go back to that picture and set x1, y1 equals cos A sine A, and x2, y2 equals cos B sine B. And let's set the result to be sine of A minus B that we just computed. Area of the parallelogram is x1, y2 minus x2, y1, which is sine A cos B minus cos A sine B. Sine of A minus B equals sine A cos B minus cos A sine B. So the mystery of the formula and its terms is traced to the area of parallelograms. Isn't that related to determinants though? Yes, but that's another story for another day.